let us discuss the computational complexity of DFT. In this session, I want to show you that how many complex additions and complex multiplications are required to compute DFT coefficients. And at the end, we will conclude that finding DFT coefficient requires so many additions and so many complex multiplications, and hence it is not technically feasible to evaluate DFT coefficients. So please have a concentration for few more minutes. I have taken a special case for n equal to 4, and then later I will generalize it. Consider a 4-point DFT xk where n ranging from 0 to 3, x of n multiplied by w raised to nk subscript 4. And this first equation evaluates the first DFT coefficient by putting k equal to 0. So put k equal to 0, x of 0 equal to summation ranging from 0 to 3, x of n w raised to n dot 0, because I have put k equal to 0. Then we have to expand this sum for n ranging from 0 to 3. So first of all, put x of 0 multiplied by, put n equal to 0, so x of 0 w raised to 0 dot 0 plus put n equal to 1, x of 1 dot 0 plus put n equal to x2 2 dot 0 subscript 4 x3 into 3 dot 0. Similarly, you can do for k equal to 1, 2, 3, and now we got the 4 coefficients. My aim is not to evaluate this coefficient, but to observe how many additions and how many multiplication goes into evaluating these 4 coefficients. And now I can note that to find the x of 0, I require this complex multiplication, because w is a complex term, total factor, it is e raised to minus j 2 pi upon n. So this is, I will say, this is a complex multiplication. So this is the first complex multiplication, this is the second, this is the third, this is the fourth, fifth, sixth, 7th, 8th, 9th, 10th, 11th, 12th, 13th, 14th, 15th, and 16th. So there are in all 16 complex multiplications. So here I'll note that number of complex multiplications for n equal to 4 comes out to be 16. Now 16, I can say it is equal to, in general, n square, because n is here 4. So for every coefficient we require 4 complex multiplications, or you can say n complex multiplications for every sample, and there are in all n coefficients, so it requires n square complex multiplication. Now next job is finding number of complex additions. Number of complex additions. And if you observe, if I have to count, I can count like this: one complex multiplication here, second here, third here, fourth here, fifth here, sixth here, 7th, 8, 9, 10, 11 and 12. So it requires in all 12 additions, complex additions, because every term is complex in above equations. And I can say that for every step 3 additions multiplied by 4 DFT coefficient, so it is 3 into 4, and this can be generalized as n minus 1 multiplied by n, because n is 4. So we have now conclude that, or we can conclude that number of complex multiplications required for DFT is n square, and complex additions comes out to be n time n minus 1. If n is 8, n square will be 64, and n into n minus 1 will be 8 into 7, that is 56. So as n increases, the number of complex multiplication and number of complex additions rise exponentially, because in every term we have n squared term, and hence as n increases, the number of complex additions and number of complex multiplications go on rising exponentially. So finding DFT is computationally very extensive, and it requires lot of time for performing these additions and multiplications. So there has to be some approach or methods which to be involved, so that these additions and multiplications should be reduced, and hence we have to discuss a transform called fast Fourier transform, which reduces these number of complex multiplications and complex additions. So in new lecture on new series will be on fast Fourier transform, which drastically reduces these number of complex additions and number of complex multiplications.